Hello everybody, Adam Lusek here, and today we're going to look at fine-tuning embedding models for retrieval augmented generation pipeline optimization. More specifically, we're going to be looking at the document retrieval step of the RAG pipeline and looking at ways of fine-tuning our embeddings to optimize the accuracy and the ranking of our expected documentation during the retrieval step. If you're unfamiliar with how embedding models work or what embeddings are and how documents are retrieved semantically for RAG pipelines, I recently released a video that'll pop up on the screen right now that outlines the entirety of what you need to know from zero to a full RAG application using vector databases and embeddings. But what got me interested in talking about this topic is I was looking into ways of actually fine-tuning embedding models just in general, and I came across a couple papers and some research reports, specifically this one on efficient domain adaptation of sentence embeddings using adapters, and also ChromaDB's report here on just straight up embedding adapters. And what both of these papers show are effectively parameter-efficient fine-tuning methods for embedding models, where you don't actually have to fully train the entire embedding model. You can create an adapter that can sit on top of it to increase your domain-specific performance. Essentially, being able to train a small amount of parameters on your own information that can then plug on top of your existing embedding model to increase the accuracy and performance of your retrieval step in your RAG application. And what interested me even more is that Chroma was claiming that they're able to get much better performance with only using a query-only linear transformation adapter. Essentially, that's just going to be an additional layer of a neural network that you train yourself on your data, and then it only plugs in at the query part of your RAG application. So when a user inputs a question and then you go to the retrieval step, that question is embedded by the embedding model, and then that embedding goes through one additional layer, which is the linear transformation here. So it's very simple, and then that is able to give you a better vector representation of your query, thus improving your performance. And the great part about this is that it's super lightweight, being only one linear layer, and then also you don't have to go through the hassle of fine-tuning your entire model or re-embedding all of your documents into your vector space. Essentially, we're just going to be training one single layer of a neural network on our data so that when a user asks a question, it's better able to place that question closer to the more relevant documents in our embedding space. And so what we'll be going over in the rest of this video is the full process of actually creating and assessing one of these query-only linear adapters for an embedding model with the purpose of trying to improve a domain-specific RAG application. One of the things that I saw in the research that we're about to apply is that a lot of the evaluation was done on standardized evaluation sets, but I thought it would be a worthwhile effort to actually test and show this approach on something that is more real-world applicable. And so, of course, the first thing is actually defining what our RAG application is going to be. And so what I did is I kept it pretty simple. I wanted a domain-specific document that would be a good candidate for question and answer flows over, and I chose Apple's 2024 Environmental Progress Report. I thought that this would be a good document because it's 113 pages long, so it'd be a good candidate for actually chunking, embedding, and then being able to run a retrieval augmented generation flow for, let's say, a chatbot application of people actually asking questions about this report. And so our goal for this quote-unquote RAG application is going to be improving the accuracy of the documents retrieved based on the questions that are commonly being asked. In your own specific setup, the type of data that you'd actually want are more the questions or the common questions that users are asking, and then pairs of the expected chunk of text that you want your retrieval system to return. So generally, what you would want to do is during the logging, if you have a chatbot RAG-based solution, you'd want to log what questions are being asked and what documents are being retrieved, and then label the actual correct documents that you want retrieved based on the questions asked, and that becomes your training data. And to reiterate, our ultimate goal is that what we want to do is improve the rate that the questions that are being asked returns the expected document or the expected chunks of text. And while this is best done on data that you've collected from, per se, user testing or user interactions, we don't have any of that in this hypothetical situation, so we'll be creating a synthetic data set. But don't worry, just because it's synthetic doesn't mean it's bad. I also got this idea from a different paper here, Improving Text Embeddings with Large Language Models, that was actually able to prove that using LLMs to actually create different text retrieval tasks, both the questions and the positive documents that are expected for those questions, can be used as training data to actually improve embedding model systems. So to set this up, I've loaded the document and split it using a recursive character text splitter that is a token-based splitter with a chunk size of 800 tokens and an overlap of 400 tokens. This is usually the standard chunking measures that I take because it's also the ones that OpenAI's file search assistant uses on default. And so after chunking all of the text, we end up with 215 chunks. And if we just take a look at one, let's say the 20th, we can see that it looks a little bit like this. And so now for the synthetic data generation, what we want to do is actually generate the potential user questions that would return each one of these chunks of text from our Apple environmental report. So what we'll be doing is actually using an LLM with a prompt, passing in each chunk of text, and then I'll actually be generating 20 questions that would likely return that chunk of text. And so the prompt that I'm passing is, you're an AI assistant tasked with generating realistic question-answer pairs based on a given document. The question should be something a user might naturally ask when seeking information contained in the document. Given, and then chunk here in brackets where I'll be dynamically inserting in each chunk. And then the instructions are, analyze the key topics, facts, and concepts in the given document, choose one to focus on. Generate 20 similar questions that a user might ask to find the information in this document that does not contain any company name. Use natural language and occasionally include typos or colloquialisms to mimic real user behavior in the question. Ensure the question is semantically related to the document content without directly copying phrases. Make sure that all the questions are similar to each other, i.e. all asking about a similar topic, requesting the same information, and then a little bit about how I want it to be output in a JSON object. And then I say, be creative, think like a curious user, generate your 20 similar questions that would naturally lead to the given document in a semantic search. Ensure your response is a valid JSON object containing only the questions. And then I create a LangChain chain here using GPT-4o mini with a temperature of 1.0 to fully create this chain. And so now when we pass in a chunk, so I'll be passing in this same exact chunk through the LLM with this prompt, what we'll get back is a JSON object of 20 similar but unique questions. So now we can see that based on this information, it came back with these 20. And a couple of them are like, what percentage less energy does the iMac consume against the Energy Star limit? Or how much energy does the iMac save compared to the Energy Star benchmarks? And so this is great. These will all be our questions that will be paired with this chunk 20, for our expected retrieval when a user asks this kind of question. And so what that comes out to is that with 215 chunks and generating 20 questions each, we end up with 4,300 question chunk pairs. So I took all of these, generated them, and then shuffled them into an 80-20 train validation set, which resulted in 3,440 training pairs and 860 validation pairs. So we'll be training our linear adapter on these 3,440 and then assessing its performance against our baseline embedding model on these 860. And then what the data actually looks like in the JSON files, which I've attached in the actual repo, which will be linked below, as well as uploaded to Hugging Face, is it's simply going to be these shuffled questions here. So it's just going to have a question and then the expected chunk of text that we want to retrieve if someone were to ask this question. So now we have our simulated synthetic data set of our retrieval augmented generation application. So all of the questions and then the expected chunk of text that we want to retrieve if someone were to ask this question. And so now what we want to do is set up our vector database so that we can simulate the retrieval and assess whether or not these questions using our embedding model actually return our expected chunk that we want. So in this situation, this is where you would set up the same vector database setup that you're using for your current RAG application, as well as using the same embedding model that you are expecting to be training with. And so, for example, I'll be setting up my go-to open source vector database, which is fitting given that we're applying some of their own technical research here, ChromaDB, which is super lightweight, super easy to use. I've used it in a bunch of videos in the past, and so this is my candidate for my RAG application. And by default, ChromaDB actually uses this specific sentence transformers embedding model, the all mini LM L6 v2 embedding model. And what it does is it maps sentences and paragraphs to 384 dimensional dense vector space. So this is our baseline model that we are hoping to improve the performance of. But to improve the performance of it, we actually need to assess its baseline performance. So let's go ahead and just create our ChromaDB instance, add all of our chunks from the Apple document to it, and define a retrieval function. And so this retrieval function will take in an embedding, run all of the semantic similarity across our vector database, and then return n number of similar results. One of the cool things about this approach using the query-only linear adapter is that it's actually able to take in any sort of embedding model because we're not actually affecting or training the specific embedding model itself. All that we'll be doing is generating the original embedding and then creating one linear transformation of that embedding. So you could use OpenAI's embedding, you could use instructor embeddings, you could use the same one that I'm using with all mini LML6, any embedding model that can create embeddings, which by nature they should be, can actually be used here, which is great, because we don't have to rely on actually being able to have the physical model itself or the compute needed to load and run and test and train the original model. So with our candidate baseline model of all mini LML6v2 and our vector database all set up, what we want to do is define our metrics that we want to optimize towards. And the two that I'll be looking at is mean reciprocal rank and recall at k, which is also known as hit rate. I have the math and equations here for what each of these metrics are and how you actually specifically calculate them, but let's talk about how you actually interpret them first. So for mean reciprocal rank, what this will show you is actually on average where your expected chunk places in the actual ranking and order of your retrieved documents. So if you retrieve 10 documents per se, and your MRR is about 0.6, the reciprocal of that, which is 1 divided by 0.6, ends up being 1.66. So on average, your document is placed in the 1.7th place out of the 10 documents retrieved. And so naturally, what we would want is the expected document to be a higher rank because that means that it was calculated as more similar in our vector retrieval system and thus can show a little bit of the accuracy here. Our second metric here, recall at k, or hit rate, is going to measure, on average, how many times the actual expected document is retrieved given k number of retrievals. So if we get an average recall at k of 0.6 given a k of 10, that means that 60% of the time when we retrieve 10 documents, our expected document is part of that retrieval. And so naturally, I would say a little bit more than rank in this case, the hit rate or the recallability is likely the metric that we want to maximize more. And so after loading the base model and then running it through our evaluation function, which is essentially just going to take in our validation data, pass all of the questions through our embedding model and our retrieval function, and then grab all of those retrieved documents, compare them to the ground truth in both our hit rate and reciprocal rank functions, and then calculate the means of those, what we got was an average hit rate at a k equals 10 of about 0.6 and a mean reciprocal rank at k equals 10 of 0.3. And so the interpretation of that is a recall at k of 0.6 is that with k equals 10 documents retrieved, for 61.16% of the queries, the correct answer was found within the top 10 result. And then for an MRR of 0.3133, the reciprocal of 0.3133 is about 3.2, indicating that on average, the first correct result appears at about the position 3.2 of 10. Our goal then now is to increase both of these metrics so that our document is both placed higher in the retrieval ranking or calculated as more relevant, and then shows up more often within our number of retrieved documents, or that hit rate there. And so now that we've got our baseline metrics to compete against, we can move on to creating and training our linear adapter here. And so to do this, I'll actually be applying directly some of the findings that Chroma found in their paper here, like using triplet loss, random negative sampling, and some of their specific hyperparameters. So let's dig into a few of these techniques. First, starting with what random negative sampling is. And so what random negative sampling is that it involves almost randomly selecting unrelated or irrelevant examples to actually show the model during the training process. And so what this will be is an irrelevant chunk of text that is going to be paired with the relevant chunk of text here. And the hope is that giving the model something that is irrelevant will make the model learn better how to distinguish between the relevant and the irrelevant information more effectively. And these negative samples come into play when we're using a specific loss function called triplet margin loss. And essentially the triplet margin loss operates on these triplets of data points. It's going to have an anchor, which is the reference sample, a positive, which is the positive sample similar to the anchor sample, and then the negative, which is going to be the sample dissimilar to the anchor. And then what the loss function is trying to do is minimize the distance between the anchor and the positive pairs and maximize the distance between the anchor and the negative pairs. Our anchor in this case is going to be the query or the question. The positive in this case is going to be the expected chunk of text, and our negative is going to be randomly sampled from any relevant document. So let's actually set up that random sampling from the irrelevant document. So what Chroma's research actually says is that through random negative sampling from completely unrelated documents, it is a cheap way to get a sizable benefit on retrieval performance. So what I did to apply this is choose some random irrelevant document, which turned out to be NVIDIA's Form 10K from 2023. So all of this financial data, which there's quite a lot of it, is not very similar to a nice fancy environmental report, but still good text data. So all we're doing is using the same techniques that we did to load and chunk the Apple document and load and chunk that. And then what I have is now a random negative function here, where when ran will continually just return some random chunk of text. And so this is how we are going to randomly sample from our irrelevant document for our triplet margin loss. And so now that we've got that prerequisite figured out, what we need to do now is make the actual linear adapter. So we're going to be using PyTorch to put this together, and the basic kind of understanding of what you need to know to understand kind of what's going on behind the scenes here is that the linear adapter is essentially just going to be one linear layer in a neural network. This looks a little bit fancy, but all it's going to be is one large weight matrix. And in our case, since our base embedding model is making 384 dimension embeddings, our weight matrix is then going to become a 384 by 384 big ol' matrix, plus then our bias vector, which is just going to be 384, giving us about 147,000 trainable parameters for this simple linear layer. And all that's going to happen then is when our original embeddings that are created by the base model are passed through, they are going to get multiplied through this weight matrix, and then the bias is going to be added to that, and that is going to be our linear transformation. The hope here, of course, is that we can do this training to tune all of the numbers in this matrix and the bias to better be able to take our base embedding model and transform it into an improved version that is able to give us increased accuracy or increases on our metrics. We can very easily represent this with PyTorch by creating a class that inherits from their base model for neural networks, setting up our single linear layer that has an input and output of 384 dimensions and 384 dimensions. That's why it's only taking the same input and output dimension as input dim, and then defining our forward pass, which is essentially going to allow us to then input our base model embedding and then run it through this linear transformation and return that output. And so now that we have that module, what we then want to do is prepare our data set. And so what we'll be doing is also inheriting from PyTorch's dataset class and creating a dataset loader that is going to be able to be used with our triplet loss. And essentially all it's going to do is take in our data, take in the base model, and take in our negative sampler. And then it is going to return our query from grabbing the question part of our data, the positive example from grabbing the chunk part of our data, and the negative from our negative sampler, embed them all using our base model, and then return the triplet of our query embedding, our positive embedding, and our negative embedding. And so now that we have a way to create a linear adapter and also a way to load our data, all we need to do is put it together into a training script. And so this training script, I'm not going to go too into detail of every single line here, since it's a pretty standard approach to neural network based training. But a few things to note here is we've included the ability to do warm-up steps, and then also we'll be using, of course, our triplet margin loss and the AtomW optimizer. The rest of it is pretty much standard of what you see with neural network based training loops. And then training the adapter is as simple as calling our training function with our base embedding model, our training data, our random negative sampler, and then all of the hyperparameters here. And for the hyperparameters, I tried to grab as many as I could from the existing research to see what they recommended. So I actually ended up training many models to try and find some good combinations, and ended up going with a triplet margin loss of 1, using, of course, the triplet loss function and negative sampling. And then all the way down here in the discussion, they recommended for linear adapters a learning rate of 0.003. So I ended up doing a batch size of 32, learning rate of 0.003, adding in some warm-up steps, only 100, doing some grad norming here, and our margin for our triplet loss of 1. And so using these parameters, I ended up training 4 different versions at 10 epochs, 20 epochs, 30 epochs, and 40 epochs. So now that we actually have those all nicely trained, let's do some assessing. And so of course, we'll be using the same validation data to run all of these results. But now we need a function to actually apply the linear adapter. And so that's what this encode query function is here. It'll take in our query, our base model, and the adapter. And what we're going to do is create the original embedding with the base model, and then we're going to forward pass that through our adapter. And that will create our linearly transformed query. And then we'll just return that, pass it through our original retrieval function that takes in an embedding, and then that's how we can apply it then to a new assessment function and see the results. And so since I saved all of these adapters as PyTorch files and also included all their hyperparameters in the file, what we can do is load it all here and print out all of those parameters. So we can see that we'll be looking at the adapter that was trained for 30 epochs. And so then after creating a new evaluation function that will now create the embeddings from the encode query function, we got an average hit rate at 10 of 0.66 and a mean reciprocal rank at 10 of 0.33, which means that we were actually very successful. That post-training, our adapter gave us an average hit rate or recall at a K of 10 of 66.7%, a percentage point increase of 4.8 over our baseline of 61.9%, which corresponds to a 7.8% hit rate improvement. We also got a mean reciprocal rank of 0.332, so our expected document tends to be placed at the 3.0 rank, compared to our baseline of 3.2, which is another 6.2% improvement on our MRR. So we can conclude that given that all of these tests were ran on our validation set, that we were able to get some very good actual improvements from training our query-only linear adapter, which is phenomenal to see. I've created a couple charts here to show just how these two metrics actually panned out over the different number of epochs from 10 to 40, the baseline being first with this line here. And we can see that while this does start actually up a little bit on both of these y-axes to show the difference a little bit more, we can see that our 30 epoch trained one actually worked the best. And then there started to be a little bit of a drop off around 40 epochs. But given the fact that we were aiming to increase our hit rate and increase our MRR, we can confidently conclude that this was actually able to make an improvement, which is phenomenal to see. And one additional thing to also bring up here is visualizing how the model's actually been fit onto the training data specifically. So this is running the same metrics, but instead of on our validation data where we would expect it to generalize its performance to unseen queries, this is actually showing how much it's actually fit to our training data. And we can see that from a baseline of 0.3 from our mean reciprocal rank up to 0.5 at 40 epochs, and then 0.6, or about 63%, at our baseline for hit rate goes up to about 78% at 40 epochs. So one of the also interesting upsides of this is that if people are asking a lot of the exact similar questions and you always want to be able to return that accurate document to them, this will also just generally work a lot better for that. And on top of that, we can prove that it can generalize to unseen queries as well. So this is a phenomenal improvement. Being able to actually train a super lightweight linear adapter that's only 147,000 parameters, not a lot in comparison to a lot of models these days, and being able to just have to apply it and plug it into and out of our queries without having to fully change our embedding model or completely re-embed all of our documents, and being able to get this actual improvement is phenomenal to see. That being said, we're able to apply some of this wonderful research to successfully optimize the retrieval step of our retrieval augmented generation pipeline through a lightweight query-only linear adapter. This is phenomenal to see, and I'll have a bunch more resources as well as all of the code here and all of the data used in the description below. If you enjoyed, consider subscribing. If you liked it, drop a like. If you have any questions, leave them down in the comments below, and I hope you have a great day. Thank you.